Welcome back everyone. So here this is our last part of the sequential circuits. In this part we will discuss about the ring counter, Johnson counter, state reduction and state assignment. So last lecture we have seen the synchronous counter, how to design the synchronous counter. Now today we will see what is a ring counter. So this ring counter is basically the simplest shift register counter. We have already studied the shift register. So the basic ring counter, here it is shown using the D flip-flops, and this ring counter can also be realized using this JK flip-flops. Okay. Now this is the state diagram and this is the sequence table, okay, of this ring counter, and this is the timing diagram of this ring counter. Okay, now these flip-flops, all these flip-flops, they are all these flip-flops, you can use any flip-flop, D flip-flop, JK flip-flop. So all these flip-flops, they are arranged in a normal shift register. Okay, that means you can see the Q output of each stage is connected to the, if you consider the D flip-flop, the Q output of each stage is connected to the D input of the next stage, right? Then, but for the Q output of the last stage of the last flip-flop is connected back to the D input of the first flip-flop. Okay, such that an array of flip-flops is arranged in a ring. Okay, that is why we are calling it as a ring counter. So in most instances only a single one in the register, and it is made to circulate around the register as long as the clock pulse are applied. So initially let us consider that all these flip-flops are set to 1. Okay, so if we write the sequence table, initially this is my first flip-flop, Q1, Q2, Q3 and Q4. So initially all the flip-flops are set to 1. Okay, so in the initial state is 1 0 0 0. Initial state is 1 0 0 0. Okay, so that means Q1 is 1, Q2 0, Q3 is 0 and Q4 is also 0. So after each clock pulse, these contents of the registers are shifted to the right by 1 bit. Okay, and Q4 is shifted back to Q1. Okay, so this sequence repeats after the 4 clock pulse. You can see 0 to 4, 0 is 1 0 0 and fourth one is 1 0 0. Again the sequence is getting repeated after the 4th clock pulse. Okay, so the number of distinct states in ring counter, that is the mod of the ring counter, is equal to the number of flip-flops used in the counter. Okay, so if you have a small n bit ring counter, it can count n bits. Okay, whereas what we have seen in case of the ripple counter, if you have n bit ripple counter, then it can count 2 to the power n bits. Okay, so this ring counter is uneconomical, okay, compared to a ripple counter, but it has an advantage like of requiring no decoder. This kind of counter, it doesn't require any decoder, since we can read the count by simply noting like which flip-flop is set. Okay, so since it's entirely a synchronous operation and requires no gates external to flip-flops, it's the further advantage of being very fast. Okay, so initially if you look at the sequence table, initially the state is 1 0 0 0. After the first clock pulse, what will happen? After each clock pulse, you can see the shift right operation is happening. So initially it is 1 0 0 0. Okay, So this Q4 is transferring its bit to D1. So this 0 is coming 1, then right shift is happening. This 1 is coming 1, this 0 is coming here, this 0 is coming here. Then again this, after the next clock pulse, then again this Q4 is coming to Q1, then again right shift, this 0 is coming here, this 1 is coming here, this 0 is coming here. Then again this Q4 is coming to Q1, again this 0 is coming here, this 0 is coming here, this 1 is coming here. Then after the next clock pulse, again this 1 is coming Q4, the Q4 bit is getting transferred to Q1, then this 0 is coming over here, this 0 is coming over here, this 0 is coming over here. Simply right shift is happening. Then after this fourth clock pulse, you can see the same sequence is getting repeated. Okay, and if this is my clock signal, this is the negative age triggered flip-flop. So like this way we can draw the timing diagram. So you can see during the after the first clock pulse, initially this Q1 was 1, right? So after the first clock pulse, it is becoming 0 till the next three clock pulse. Q1 will be from 1 to 3. From the next three clock pulse, this Q1 will be 0. Then again, once the fourth clock pulse is applied, then Q1 will become 1. Likewise, we have to draw all these states, the timing diagram of all these flip-flops based on this table, okay, depending upon this clock age. Alright, so next we will go for the Johnson counter. What is Johnson counter? This counter is also called the twisted ring counter. Okay, so this counter is obtained from a serial in serial out shift register, and by providing feedback from the inverted output, you can see the Q4 bar output of the last flip-flop to the input of the first flip-flop, right? The Q output of each stage is connected to the D input of the next stage, but the Q bar output of the last stage is connected to the D input of the first stage. Okay, therefore we are calling it as twisted ring counter or Johnson counter. Okay, so this is the logic diagram of a 4-bit Johnson counter using both D flip-flops and JK flip-flops. This is the state diagram, this is the sequence table, and this is your timing diagram. Okay, so initially, let's say all these flip-flops are set. That means initial stage is 0 0 0 0. All this is first flip-flop, second flip-flop, third flip-flop, fourth flip-flop. Okay, after each clock pulse, the level of these Q1 is shifted to Q2. Okay, and Q2, then Q2 to Q3, then Q3 to Q4, and the level of the Q4 bar to Q1. Okay, and the sequence given in these table, it is obtained. Okay, so this sequence is repeated after 8th clock pulse. You can see over here, after 8th clock pulse, again it is becoming 1 0 0 0. Okay, so if you have a small n flip-flop, a Johnson counter can have 2n unique states, and it can count up to 2n pulses. So it is a mod 2n counter, and it is more economical than the normal ring counter, but it is less economical than the ripple counter, and it requires 2 input gates for decoding regardless of the size of the counter. That is why, that means it requires more decoding circuitry than that by the normal ring counter, but less than that by the ripple counter, and it represents a middle ground between the ring counter and the ripple counter. So if 0 0 0 is my initial state, how it will count? See here, let's say all the states are 0 0 0 0. Okay, so when the clock pulse is 0, when you haven't applied any clock pulse, so when the first clock pulse is applied, what will happen? When the first clock pulse is applied, what will happen? Q1 will change to 1. Q1 will change to 1, and then this Q1 will change to 1, and then the level of Q1, it will get shifted to Q2, Q2 to Q3, Q3 to Q4, and then Q4 bar, it is going to the Q1. If Q4 is 0, Q4 bar will be 1. Then again this Q1 is shifting to Q2, Q2 is shifting to Q3, Q3 is shifting to Q4. Again this Q4 bar, that means here 0 means 1 will come to Q1. Then again Q1 is shifting to Q2, Q2 is shifting to Q3, Q3 is shifting to Q4. Again what will happen? This Q4 bar 1 will come to Q1, then Q1 will get shifted to Q2, Q2 will get shifted to Q3, and Q3 will get shifted to Q4. So this is how it will proceed. After the 8th clock pulse, you can see the counting sequence will get repeated. And from this sequence table, we need to, depending upon the negative edge of the clock pulse, we need to draw the state of each flip-flop, the output of each flip-flop. Okay. Next we will learn about the state reduction and the state assignment. Okay. So the state reduction technique, it is basically avoids the introduction of redundant states. We have previously seen the state diagrams, right? So this state reduction technique, it basically avoids the introduction of redundant states, and the reduction in redundant states, it reduces the number of flip-flops and logic gates, reducing the cost of the final circuit. So two circuits are said to be equivalent if every possible set of inputs generated exactly the it generates the same output basically, and the same next state. When two states are equivalent, one of them are removed without altering the input-output relationship. So here the reduction technique has been elaborated with an example. Okay. So first there are two steps. First step is we need to determine the state table for the given state diagram, and next we need to find the equivalent states. Okay, so in equivalent states, every possible set of inputs generate exactly the same output and the same next state. So in the given circuit, there are two input combinations, either 0 or 1. Okay, so looking at the state table for two present states that go to the same next state and have the same output for both input combinations, we can easily find that states A and C, they are equivalent, and also B and E, they are equivalent. This is because both states, the A and C, they can go to states and B and D, and they can have the same outputs. Okay, same outputs 0 and 1 for the inputs x0 and x1. Okay, what you can see here, how many states we can see here in the state diagram, and in the state diagram what we are representing it in terms of the number, in terms of the alphabets A B C D E F. Okay, but usually we represent it in binary number. Okay, but here we are just using the alphabets. So total 1 2 3 4 5 6. Okay, total 6 present state. Okay, now here it is my next state and this is my output. Now how we need to draw it, you can see over here, when when I want to, suppose I am here in A, I want to go to B. So when the input is 0, if I want to go from A to B, input is 0 because X is 0. If I want to go from A to B, X is 0. So my input is 0. And what is my output? Output is also 0. That is why I have written 0, 0. Okay. Now, if I'm at A, I want to go to D. Okay. I am at A, I want to go to D. So what is the input? X1. And what is the output? 1. So it is 1, 1. Similarly, if I'm at B, I want to go to E. So I'm at B, I want to go to E. What is the input? 0 at that time. What is the output? 0, right? And if I'm at B, I want to go to F. What is the input? 1. What is the output? 1. So this way, if I am at C, I want to go to B. What is the input? 0 and output 0. So 0, 0. If I am at C, I want to go to D. What is my input? 1, output 1. That is why 1, 1. Okay. Similarly, we have to do it till F. This is how we need to draw the state diagram. Okay. Now, this state diagram, suppose once this state diagram is already there, from this state table, what you are observing from this state table, you can see this for A and C, these input combinations and output combinations, the next state and the output combinations for A and C, it is same. So we can easily remove one from them, right? Similarly, for B and E, the input combinations and the output combinations are same. We can easily remove one from them. So previously we had 6 states. We are removing 2 states. So we are left with 4 states now. A, B, D, F. So further, no more reduction is possible. So this is our final state table. So from this state table, suppose this is the state diagram, and from this state diagram we need to get the state table. Okay. So now this is my state table. So from this state table we can easily draw the state diagram. Suppose now A, B, D and F are there. A, B, D and F are there. If I am at A, I want to go to B. What is my input? 0 and output 0. So 0, 0. Likewise, this will be my final state diagram. That means what will happen? First, every possible set of inputs, it generate exactly the same output and the same next state. So there are 2 steps we need to follow here. We need to determine the state table for the given state diagram. This state diagram will be given to you. We need to find the state table. We need to find the state table. We need to see if state reduction, we can reduce any states or not, if the redundant states are there. Suppose for here A and C, these input and output combinations are same, so we can just keep one state. 2 states are redundant, right? So after these, we can see no more reduction is possible. So this is my final state table, right? So this is my final state table. Okay. So, and this is my final state diagram. Okay. Now, what is the state assignment? So, in state assignment, the process of assigning binary values to the states of the sequential machine is known as the state assignment. The binary values are to be assigned to the states in such a way that it is possible to implement the flip-flop input functions in using the minimum logic gates, and the output values of the physical devices are referred to as the state variables. And what are the rules for your state assignment? First rule is to states having the same next state for a given input condition should have assignments which can be grouped into logically adjacent cells in a K-map. And rule number 2 is states that are in the next states of a single state should have assignments which can be grouped into logically adjacent cells in a K-map.